All right, gang. If after watching this week's videos and you start doing your assignment on means, dealing with the central limit theorem and some probability, if you're still a little bit confused, it means that you're nothing less than more than having a look at it than normal. No pun intended. The purpose of this video is to kind of bring a more of a central focus to the types of problems, the concepts that you're going to use on your assignments. So what I've done in my math lab, again, depending on when you're taking the class, this was put up in the summer. I want to work some demo problems for assignment number 9, which is the one on means. So let's do it, okay? So I think there's only 4 or 5 questions, only 4 questions. So we'll talk this through together, and I'll not only do the problems, but we'll do a little bit of teaching along the way. If I can get back in here, okay. So question number 1 says the distribution of the scores on a certain exam is a normal distribution with a mean of 50, standard deviation of 10, which means the exam scores are normally distributed, mean of 50, standard deviation of 10. Sketch the curve and label on the x-axis the position of the mean plus or minus 1 standard deviation, the mean plus or minus 2 standard deviations, and the mean plus or minus 3 standard deviations. Well, if we have a mean of 50, it means our distribution has to be centered at 50. So the only one that's not centered at 50 is C, so C can't be right. The standard deviation of 10 says when we start in the center at 50 and add the standard deviation, which in this case is 10, we should get 50 plus 10 is 60, and 50 minus 10 is 40 on the other side. So guys, pretty clear here that the correct answer is B. All right, B, find the probability that let's continue. Okay, what is the probability that a randomly selected score will be greater than 60? Use the empirical rule. The probability that a randomly selected score will be bigger than 60 is about, well guys, if you, let me go back over to the to this. Remember that in a normal distribution, if we have the mean in the center and the mean minus a standard deviation and mean plus a standard deviation, that approximately 68% of the scores are between 1 standard deviation below and 1 standard deviation above. Now that means that we have 34% in each of these halves, because 34 plus 34 gives us 68. Essentially what this question is asking is approximately what percentage is above 1 standard deviation above the mean. Now let me go back and make sure that I'm reading this correctly. Using the empirical rule, what's the probability that a randomly selected score will be greater than 60, which is exactly what I'm teaching over here. Well, if you think about it, we have from here down, we have 50% of the distribution plus the 34 that we have here. So 50 plus 34 gives me 84. Well, I know that 100% of my distribution scores are encompassed with the area under the curve. So if I take 100 minus the part that I'm already accounted for of 84, I'll get 16. So depending how they want us to put this in, it looks like they want us to put it in as a percentage, the answer would be 16. All right. Which graph shows the distribution with the region shaded under the normal curve whose area corresponds to the probability that a randomly selected score is greater than 60? Well, it needs to be the area to the right because it's above, greater than, and it needs to start at 60. So guys, clearly B would be the correct answer in this situation. All right, don't you wish it would stay that easy? All right, the mean age of all 2547 students in a small town is 22.8 years, standard deviation 3.8 years, and the distribution is right skewed. A random sample of 4 students' ages is obtained. The mean is 23.4, standard deviation 2.9. Find mu, sigma, the standard deviation for the sample, the mean for the sample. Well, guys, mu is the mean for the larger group. In this case, it's the all students at a small university. So mu is going to be 2547. The standard deviation of the population is given as sigma, which is 22.8. The sample mean is, in this case, the mean of these only 4 students who created this random sample. Well, that's 23.4. And the standard deviation is 2.9. So let's check it. It's going to be right. Oh, it's not right. At least one. What do we do here? Oh, shoot, guys. 2547 is how many students are in the population. This should be 22.8. Well, I had a bonehead moment right there. Hopefully you guys were screaming at me to let me know that. And 3.8. Trust me, guys, I know what I'm doing. I just can't see. All right, is mu a parameter or a statistic? Well, anytime we have a Greek letter, we're looking at a parameter. So the value of mu is a parameter because it is found from the population. Are the conditions for using the central limit theorem fulfilled? Well, guys, what we need for the central limit theorem is we need a sample depending on the textbook. Your textbook goes with 25. Most textbooks go with 30. So the conditions aren't used. No, because the random sample independence is not satisfied. Well, we have a random sample, and we have independence, or at least we can assume that. B, no, because the big population condition is not satisfied. Or is it no, because the large sample condition is not satisfied? Well, guys, we don't have 25, so the large sample condition is not satisfied. What would be the shape of the approximate sampling distribution of many means, each from a sample of 4 students? Well, since the distribution is right skewed, I'm going to say that the distribution of means would also be right skewed. Now, what would we need to do to make the distribution normally distributed so we can use our calculator to calculate probabilities? We would need a sample size of about 25 or 30. Again, depending on the textbook, 25 for your textbook, 30 for most other textbooks. All right, so the average income of a certain region in 2013 was $51,000 per person. The standard deviation is 26,000. Distribution is right skewed. Suppose we take a random sample of 625 residents. So we've got a random sample, good. 625, bigger than 25 or 30, doesn't matter, good. We want to find the probability that the sample mean will be more than 2,080 away from the population mean. Use the technology output below to complete parts A through C. All right, so there's what we have, and I'm going to move that over there so we can answer our questions. So why is the distribution normal and not right skewed like the population? Since the conditions to the central limit theorem are satisfied, the distribution is normal because the sample size is large. Why is the z-score 2? Well, if we look at 2080, I wonder why that's going to be. Well, since the standard error of the sampling distribution of the means is what? Well, guys, to find the standard error, we have to take the population standard deviation. So let me go back over to the piece of paper and show you. All right, so the standard error for these types of problems. Well, I'm having a technology issue, ladies and gentlemen. Let's see if we can get this to focus in a little bit better. So the standard error in these types of problems is the population standard deviation divided by the square root of n. Now, typically the notation you see for this is sigma sub x bar. So this is a fancy schmancy way of saying it's the standard error of the distribution of sample means. Guys, I need to get that better because it's going to drive me crazy. Okay, so for our problem, the population standard deviation was 26,000. And we had 625 residents. So I'm going to put divided by the square root of 625. So all I did there is I put the population standard deviation value here, the square root of the sample size, which is 625. So if we take 26,000 divided by the square root of 625, close up the parentheses, you'll see that we get 1,040. Now, what's going on with the question here? The standard error is 1,040. I don't think we need to put in the dollar sign. Well, yeah, it's out front. So the z-score is 2 because 2080 is double. 2 standard deviations away from the mean, which is mu equal the mean of the population, which is 51,000. All right, let's check our answer. Got a lot going on here, so be easy to do a typo. What is the probability that the sample mean will be more than 2080 away from the population mean? Well, guys, gives it to you right here, doesn't it? It's the p. It's 4 places, 0.0455. Now, what I want to know, and I want to go back to this question, what if we didn't know that? What if it wasn't intuitively clear that we could use this icon to calculate this value? How could we use our calculator to calculate the value? Well, let me show you how we do that. So let me get out of this and make this over here where we can see what we're doing here. All right. Now, what we would need to do there is we would need to understand that in the sampling distribution, we want 2 standard deviations away, so we want this part of the area under the curve shaded because it corresponds to the probability that we're looking at. So we've got our mean. The mean up to 2 standard deviations is 2080. But what if this wasn't intuitively clear and we wanted to use our calculator to find out this probability plus this probability? Well, gang, what we could do, and I'm not showing you this to confuse things, I'm just showing you this to try to get you thinking not necessarily about z-scores, but thinking about the population distribution. So guys, in the population distribution, we have a mean for the sampling distribution of 51,000. We have a standard deviation, as we saw earlier, called the standard error of 1,040. What we want to know is in our distribution, with a mean of 51,000 and a standard deviation of 1,040, what is the area more than 2,080 away from the mean? Well, guys, if we add 2,080, we get 53,080. If we subtract 2,080, we get 48,920. Now let me get my calculator turned on and so we can calculate our probabilities. Now, because of symmetry, we know that if we calculate one of these areas, that all we have to do is double it and get the same area on the other side. Well, I'm going to find this area right here. And I'm going to use normal CDF, which I've shown to you before. My left bound on this is 53,080. I'm going up to infinity with a mean of 51,000 and a standard deviation, which becomes the standard error because I'm working a distribution of sample means problem of 1,040. Now, when I get that, I get 0.02275. I multiply that by 2 because I have to account for the area down here that I calculated will be equal to the area that I calculated above. So I get 0.0455 with technology, which matches up perfectly with what I got using the empirical rule. Now, the empirical rule is fine. We had a problem right here that looked at 2,080, which was perfectly twice the standard error. But something I want to throw out to you guys is, what if it didn't fall nicely on that twice the standard error? For example, what if we wanted to know the in this sampling distribution, mean of 51,000, standard deviation 1040. What if we want to know the probability of collecting a sample mean of 54,000 or higher? Well, we couldn't use the empirical rule because this 54,000 doesn't fall nicely on 1, 2, 3, 4, 5 standard deviations above the mean. Standard errors above the mean. It falls in between. So guys, in this situation, we would have to use technology to work that problem. So guys, that's all I got. This is, at least I think it is. Let me see if we've got another problem here. Yeah, we do have another problem, so let's work it before we go on. So the average income in a state was 78,000 per year. Suppose the standard deviation is 30,000. Distribution is right skewed, as you would expect for anything dealing with money. Suppose we take a random sample of 100, bigger than 25 or 30, so life is good. We can work this problem. What value should we expect for the sample mean? The expected sample mean is always going to be the population mean, because the sample mean is an unbiased estimator of the population mean. Now, how do we know that? Well, we know that back, let me again get over, pull this up. We know that from something I taught you earlier that says the mean of the distribution of sample means is the population mean. Unbiased because it's equal to. Okay? And unbiased because I told you it's unbiased. So we're going to check that. It's going to be right. What is the standard error for the sample mean? Well, gang, to do that, we're going to have to take the, let me see if I can get a couple of things going on here. Yeah. The standard error in this case, of course, we got a new problem, so we need a new sheet of paper so we don't get too cluttered. So again, the standard error for this type of problem which is sigma divided by the square root of n. Sigma in this case is 30,000. And I can't see n because it's over here. Looks like n is 100. Again, the standard error would be 3,000. All right. Well, I guess it's it, isn't it? Okay. I thought it would have us calculate a probability. I'll tell you what. Let's do that. Let's say that there is a C, and this will happen, gang. What is the probability? So let's say we have a, again, our sample size is 100. It's given in the problem. What is the probability we select a random sample with mean equal 82,000. So what is the probability we select a sample mean, I should say higher than X bar of 82,000. So what we would do here is we would look at our distribution of sample means. It's going to have a mean of 78,000. Our standard error, as we saw earlier, is 3,000. 82,000, by my design, doesn't fall nicely on one standard deviation or two standard deviations above. So I need a picture. Since I want higher than, it's going to be this area. And I need technology. So technology is going to be like this. Use normal CDF as I've tried to teach you. And if you're watching the videos like you need to, you've seen this before. If not, then you need to go watch them. So I want what? 82,000 and above. With the mean, which is what, 78,000. With the standard deviation, which we call the standard error, which is 3,000. And guys, we're done. The answer would be 0.0912. Now, why don't we need to multiply it by 2 like we did the previous time when we used our calculator to find the probability? Well, because we're not doing what's called a two-tailed test. We're simply looking at a random sample higher than 82,000. If we looked at it like the last time, where we had clearly an above or below type of problem, then we'd have to multiply it by 2. In this case, we do not need that. Now, what if this said lower than 82,000? What would I need? Well, my shading would be different, wouldn't it? My shading would be this part And how would I work that problem? Well, I would go normal CDF. And I would start at negative infinity up to the 82,000 with my mean of 78,000 and a standard error of 3,000. Now you're going to see something. You're going to see that if we had just taken 1 minus the 0.0912 in the previous problem, the one up here, we would have got the same answer. Because again, the area under the curve is always equal to 1. Guys, I hope this helped. I know this is getting more challenging. It's a lot more challenging than the things that we've been doing so far, because when you kind of lump the central limit theorem with normal distributions, along with confidence intervals and hypothesis testing, I know there's a lot going on. Some of you are just going to have to rewatch some of the videos. And I'll tell you, some of you are starting too late. I'm getting emails on, 4 or 5 hours before assignments are due. And it's just clear to me you guys haven't watched the videos yet and you're struggling. That is just not the way that the course is laid out. If you were taking this in the classroom, you would be, okay, you would be spending about 3 to 4 hours a week, depending on whether you're taking this summer, fall, or spring. If you're taking it in the fall or spring, you'd be spending about 3 hours a week in the classroom. If you were taking this class in the summer, you'd be spending 4 hours a week plus your assignments. So, the expectation that you're going to watch 4 hours of videos in the summer, I mean, that's something you should have come to the table knowing and not be surprised by that. So, guys, that's all I got. Take care. Have a good one.